So we'll be back. So I hope everyone has a very nice break where you guys didn't have to do any classwork at all. So today we're gonna be back to the final piece of materials for before midterm 2, which is alternating series, absolute convergent, ratio and root test, and then finally, similar to midterm 1, we have strategies of testing series. So I kind of like just go over everything without recording it. So now I'm kind of recording it again. So just quickly go over it. We have the alternating series test for the section 11.5. It's the saying if you have an alternating series, and this is the form, it's -1 to the n minus 1 multiplied bn. So bn is kind of like an always positive term because it's just putting out of the -1 to the n minus 1. So you have based on the alternating series test, it says if this is the decreasing function sequence, so 0 is bigger than is smaller than or equal to b to the n plus 1, smaller than or equal to bn, so a decreasing sequence with limit of the n term in the sequence is equal to 0, then you have a series is convergent. Note that this bn is the always positive part, so actually you include that thing in. And then you have alternating series estimation theorem. So to use this theorem, you have to first prove that the series is convergent by the alternating series test. See here, that is the first condition so that you can use it. And then second one is just use the estimation theorem. So if you want to use this theorem, first thing you should always do is to make sure that it's an convergent theorem, because as sometimes you wouldn't when you don't get the answer, you will understand why, like maybe the estimation theorem is not applicable because of your series. So the estimation, after you get that, the estimation theorem will show you just the arrow from the n term, from the n sum, say n equal 3, so like the third sum, maybe like s sum, s3 minus fn, which is the nth partial sum, so the limit of the sum. So the arrow from the current sum that you are at the value of n, say n equal to 3 or 5, compared to the limit of the sum, that arrow is smaller than or equal to the n plus 1 term in the sequence. Note that this n plus 1 term is the always positive part of the sequence. Now some of the problems they can ask you in this section is, so find the minimum number of terms such that the arrow is smaller than or equal to some value. So first one, you have to prove that the alternating series is convergent and use this estimation theorem. Another thing that they can ask you is that maybe like which series is absolutely convergent, conditionally convergent, not divergent. This is gonna be the part we'll cover in the next one, but what if it's asking that and you're given an alternating series, most of the time you have to use the alternating series test to kind of like investigate it as well, but it's not the always case. So let's go to the first example. So it's practice problem 1a. Evaluate the convergence of this series. Now, is this a weird one again? Always when you see a weird one with a series, make sure that you investigate the term. So you have sine of n plus half pi with n equal to 1, 2, 3, 4, and so on. It's going to be -1, 1. You have 3 pi over 2, and then you have this one 5 pi over 2. So -1 and 1, and you continue to it just keep flipping back and forth between -1 and 1. So to do this, kind of like your series is now rewritten as -1 to the n divided by square root of n plus 2. Now, why do I know it is to the n and not to the n minus 1 or n plus 1? Well, you can put it as n minus a. When you put in n equal to 1, you have -1 to the 1 minus a is equal to -1. So 1 minus a is equal to 1. This is the easiest way. You can have like equal to 3, but then you're going to have a be like a negative number. So you're going to have a equal to 0. So this one is just going to be -1 to the n over square root of n plus 2. Now we have this series. Now using the alternating series, we can figure this one out. So alternating series tests, if you want it to be convergent, you need a decreasing function. So you have the n plus 1 term, which is the positive part, is going to be n plus 1 over square root of n plus 3. And you know the fact that because the denominator is always bigger, you will always need to have you always gonna have a decreasing function. Like this term is gonna be smaller than this one. And then you have limit of n approaching infinity of 1 over square root of n plus 2 is 0. So then you have this series is convergent by alternating series test. So you have two conditions satisfied. So that's a pretty easy and basic one. Just put it there so that you guys kind of like know what kind of questions you might be asked in this section. And so let's go to example 2. Find the minimum number of terms must be added so that the sum of the series is of error of that. So as I said, first thing is to prove that it's convergent. So again, you have 0 is smaller than 1 over n plus 1 cube smaller than or equal to 1 plus n cube. Again, because of the same reason, the denominator is bigger for the n plus 1 term. And then you take limit of n approaching infinity, 1 over n cube. This is going to be 0. So you have this series is convergent by alternating series test. Now you want to use the estimation theorem. You're going to have the error is smaller than or equal to b to the n plus 1, smaller than or equal to 0.008. So then you have 1 over n plus 1 cube is smaller than that. Or you have n plus 1 cube is smaller than or equal to 5 cube, which is 125 as well. Then you have n plus 1 is smaller than or equal to 5, or n bigger than or equal to 4. So your answer is the fourth sum of the series is of error smaller than or equal to this from the nth partial sum, or from Sn. So just two steps, and it's kind of very basic for this sections. So we're gonna go to 11.6 absolute convergence ratio and root test. So absolute convergence say a series is absolutely convergent if the series of its absolute value is convergent, and it's conditionally convergent if the series is convergent, but not absolutely convergent. And you're gonna see this is where we're gonna use the alternating series test in. This is a little bit abstract with this definition, but we want to see it in the example. When we have the theorem saying if a series is absolutely convergent, then it's definitely convergent. Then it's convergent. And then we have the ratio and root test. So the ratio and root tests are very, very helpful in some cases. It's just going to take like one expression by finding that limit at n approaching infinity of the absolute value of n plus 1 over an, or the absolute limit of n approaching infinity, the nth root of an. If you just, in these cases, if you find that limit is more than 1, it is absolutely convergent. Bigger than 1 is divergent. If it's equal to 1 is inconclusive. Now, the note is that if it's equal to 1, there's nothing you can do with ratio and root tests, so don't use them. It's not helpful at all. But another thing to note is that when you have using ratio and root tests and you get L bigger than 1 and you have a divergent series by absolute value, but the series that you given, say an is alternating, then you can use the alternating series test to prove that the alternating series is convergent and therefore it's conditionally convergent. You're gonna see here soon. So example 3, find the convergence of this. So there are two ways that you can approach this. The way that we learned before is using test of divergence. You take limit of n approaching infinity of an is going to be limit of n approaching infinity, negative 1 to the n, 5 to the n minus 2n over 4n minus 3n. Now this one, you know for the fact that it's going to be limit n approaching infinity, negative 1 to the n, 5 over 4 to the n minus 1 over 2 over 4 to the n, 1 minus 3 over 4 to the n. Now as n approaching infinity, this one approaching 0, this one is 0, but this one is approaching infinity, and you have a negative 1 to the n. So our limit is gonna fluctuate between positive infinity and negative infinity as n approaching infinity. So this one is going to be divergent by test of divergence. So remember, test of divergence say for any series, if you find the limit of n approaching infinity of the sequence, and if all of the term, and if that limits that is not giving you a number different than 0, then it is divergent. But now we can use a ratio test to solve this. Why do we don't use root test? An easy thing is that when you take the nth root of the absolute value is 5 to the n minus 2 to the n divided by 4 to the n minus 3 to the n. You can try this, but you're going to notice the fact that it's not leading you to anywhere, because the nth power is to every single term. It is not like n square root of something to the n. Then this thing will be helpful because it's going to give just the thing inside that bracket. But if you have the n roots individually like this, it wouldn't really give you anything. So ratio test is where you find limit of n approaching infinity, absolute value of a to the n plus 1, the n plus 1 term, and over the n term of a sequence. And you take absolute value of that. So you're going to have 5 to the n plus 1 minus 2 to the n plus 1 divided by 4n plus 1, 3n plus 1. Multiply. This is a little bit tedious, honestly. But there's one way related to this I want to show you. So, to do this, give me a second. I have a look at my notes again. So you have 5 to the n plus 1 multiply 4n divided by 5 to the n multiply 4 to the n plus 1. So basically I take all of the most powerful term of every part out. So what I have inside is 1 minus 2 over 5 to the n plus 1 and then you have 1 minus 3 to the fourth to the n. And then you have here 1 minus 2 over 5 to the n, and then 1 minus 3 to the fourth, n plus 1. Now, having said that, as n is approaching infinity, all of these 4 brackets is gonna approaching 1. So you don't really need to care about them. About this part, it's going to be limit of n approaching infinity, 5 to the n multiply 4 to the n. I just rewrite 5 to the n plus 1 as 5 multiply 5 to the n. And you have 5 to the n multiply 4 with 4 to the n. So these two cancel out, and then what we have left is just 5 over 4. And this is bigger than 1. So again, it's give you that is divergent. Now, as I said, when you're given alternating series, and this is and you use ratio test and it gives you divergent, the next step you're gonna do is to see if it satisfy the premise of the alternating series test, and if it does, you're gonna be able to prove that it's divergent. No, convergent, conditionally convergent. But here, if you use an alternating series test, it's gonna give you this is an increasing function, and then it's because you're gonna be able to find it based on just look at that one. And limit of n approaching infinity of an is infinity, because it's gonna approaching 5 over 4 to the n. So this is also divergent by alternating series test. So our final conclusion is that it is completely divergent. Now, that is kind of like, it looks tedious, but the step is pretty straightforward. Now we have example 4. Determine if the series is absolutely convergent or conditionally convergent. Now you have limit. First of all, I want to say here, if you can prove the fact that a series is, I think it's will best if you just use a ratio root test. You have limit n approaching infinity, the nth root of the absolute values of n term in the sequence. Then you have this one is equal n to the n squared minus 1. And this one, you know the fact that it's approaching 0 for sure. And 0 is smaller than 1. So, by root test, the series we'll say this thing should start at 2 instead of 1, is absolutely convergent. So really easy. That's why I say ratio and root test can be really, really helpful sometimes, but when that limit takes them to 1, it's not helpful anymore. So that's all I have for 11.6. Now we're gonna go to 11.7, which is kind of like a summary of everything we learned so far in midterm for exam 2. So strategy for testing series. So the first step, whenever you're given any question, is skim through the questions to see if you can immediately use test of divergence or not, just like our example 3 earlier. Be careful with test of divergence, as I note in that section as well, that if you have that limit of n approaching infinity of the n term in the sequence b0, you know nothing about the series. You cannot conclude that, okay, because it's equal to 0, it's convergent. You cannot conclude that. The only thing that we know is that if that limit is different from 0, then it's divergent. If you have a p-series, geometric series, a telescoping series, then you can just use that property without using any kind of like comparison test or like alternating series test, integral test, ratio and root test to prove it at all. The last one is that if you have an alternating series test, easy, you can apply an alternating series. Now, second one, if none of those things work, if the n term of the series is complicated, choose a test based on that. If you have a rational function, most of the time you're gonna use either comparison test or ratio test. If you have something raised to the power that depends on n, use a root test. Finally, if it's easily integrable, like something like, we look at that before, like x to the n ln of x or something, then, or if you have no test that work with it, like even the limit comparison test doesn't work, or ratio and root test doesn't work, or alternating series test doesn't work, then that's when you use integral test. Because integral test is usually very tedious in the part you have to find what is the value of that integral from, may I say, 2 to infinity or 1 to infinity. So it's usually the last one we want to try on. And one thing to note with integral test, which I also said in that section when we go over integral test, is that even though you have to find that integral, the sum of our series doesn't equal to that integral at all. Even say if you get it as a number, it's not the value of the sum. Now, number 3, just a quick note over there. If one fails, try another one. Do not freak out. You've learned the materials for midterm 2, and this is a midterm. This is not like a talent test or something, so it's not going to be super crazy and asking you about things you have no idea about. So if this one fails, you have other tests to try, so don't freak out, just hang on there. And the last one is be careful on what the question is asking, if it's convergent or absolutely convergent. Because when it talks about absolutely convergent, usually you're going to use ratio and root test, not just the comparison test. But if you can prove that the absolute value of that series, say you're given this an, and if you can prove that this series an is convergent, then it's absolutely convergent based on the definition of what is absolutely convergent. Now, having said that, I have put all of the tests over here, just for the purpose of review when you guys look at the slides, and then I think it's a very helpful keynote. I also see this in your slides in the previous semester. I don't know if she still keep it, because she doesn't tell me if she changed your slides, so I didn't really look at it again. But this is also the test if the steps if you are asking if the series is absolutely convergent, conditionally convergent, or divergent. So first one is try the ratio test or root test. If it doesn't work, then go to step 2. Test the absolute value for convergent, or if it converge, you're done. Or if it's absolutely convergent, if it's divergent, then you can try testing the original series. Say maybe it's the alternating series, and alternating series test may make it conditionally convergent. So let's go to example 5. Let's see what I have here. So example 5. Now, first one, when we look at this, the first thing I'm going to do about is that this is a rational function, and it's pretty simple. So I can, and if you glance through it, the fact that as n approaching infinity, this limit is not 0. It's 3/5. Easy, right? Because it's a very simple, and you can just look at the highest power in the numerator and denominator. So I have limit of n approaching infinity of 3n over 5n plus 1 is 3/5. Different from 0. So this is divergent by test of divergent. And you don't have like an alternating series here, so you wouldn't do like the extra step. But this is divergent. Second one, now you're given an alternating series. So we have to, here you have a rational function. So you can use the ratio test or the comparison test. in this case, because we have like kind of like a complicated denominator, no, the numerator, so I will you go with comparison test for I will go with comparison test for to save time. So back up here, the comparison test give us if you have a convergence series and you compare with that, then okay, so you have e to the 1 over n cubed. This is always bigger than or equal to 1, because you have, because not one, just 1, it's 1 over, give me a second, it's kind of like overload the computer right now for some reason. I'll just okay, now we're back. So this one is not just 1, is 1 over n cubed. This is because you have e to the 1 over n, with n going from 1 to infinity. So it's e to the 1, e to the 1/2, which is square root of e to the 1/3, and so on. So this part as e at n approaching infinity, e to the 1 over n is going to be e of 1 over infinity, which is e to the 0, which is going to be just 1. Now, you know that this is bigger than or equal to that, and then you can also put it as e to the n cubed. So this is squeezed between these two. You know, the fact that the first value is e and every term after that is smaller than that, so it is squeezed between that. So, and you have both of them are convergent, so you're gonna pick this direction. When we have e to the series is convergent by p series, because n equal p equal to 3 here, so it's convergence by p series. Therefore you have this series e to the 1 over n cubed is convergence by direct comparison test. Now you have the absolute value of the series is convergent. The absolute value of the sequence of a series make up the series is convergent. Therefore, it is absolutely convergent. Be careful, if you have the absolute value here is divergence, that's when you're going to use the alternating series test to see if it can be conditionally convergent or not. But here, since you look at the absolute value and it's convergent already, it's absolutely convergent. You can immediately conclude that. Now, number 3, again, we're going to have another comparison test here, or you can do limit comparison test if you want. So always with trig function, you know the fact that it's always squeezed between -1 plus 2 or 1 plus 2. All we have is simply between 1 and 3. Now, either if you're talking about 1 over 3 to the n or 3 over 3 to the n, both of them are convergent by geometric series. But so you know that it's convergent, so you're gonna pick this side if you want to use direct comparison test. So you have this part and you have this series is convergent by geometric series of r equal to 1/3. Clearly you can see it here. Then you have this given series 2 plus cosine n over 3n is convergent by direct comparison test. And also here we're talking about the absolute value again because the series is always positive. It's always only squeezed between 1 and 3 for the numerator. So the entire thing, 3 to the n is always positive. So the entire thing is always positive. So itself is equal to its absolute value. So 2 plus cosine n over 3n is equal to itself because of the absolute, because this is a positive series. So this is absolutely convergent. Again, if you have any problem figuring these things out when you're doing the review or listen to these sections, feel free to contact me. I don't have much things to do. A list like not as intense when I was in Penn State. So feel free to contact me if you have any questions. Now the last two exercise for this sections. Determine again if each series is absolutely convergent, conditionally convergent, or divergent. Now again we have cosine of n pi. I think we did this thing before. Is negative, just negative 1 to the n if n stand. So this is an alternating series. Now if you use now you have this series, the absolute series, 1 over square root of n. This is divergent by p series because p here is equal to half, smaller than 1. But then I told you if you have an alternating series and you look at the absolute value is divergent. Now come back to the alternating series, the original alternating series, and use alternating series test to see. So we have, that is the first one. So the second one is that you use alternating series test. So you have one, it's a decreasing function. Again, because of the thing happened in the denominator. And you have limit of n approaching infinity of 1 over square root of n is 0. So this is, so my conclusion is the original series is convergent by alternating series test, but the absolute value is not. Therefore, you concluded that it's conditionally convergent. So this is a very good example of what I meant throughout the last 5 or 10 minutes. So if you look at the absolute value of a series and it's divergent by p series, and you give an alternating series, so go back to the original series, use alternating series test, and if it's convergent, then it's conditionally convergent. If it's divergent as well, the entire thing just gonna be divergent. Now the last one, again another alternating series, but we have the nth root. So we can use a root test. Limit of n approaching infinity, nth root of absolute value of an, which is going to be limit of n approaching infinity, 3m minus 5 over 4m plus 3. This n is 9. And this one, at n approaching infinity, clearly is 3 over 4, smaller than 1. So the series is absolutely convergent by root test. Again, this is pretty straightforward. If everything like this is ever gonna give you a divergent, go back to go back to the original series because it's, and use alternating series test because here we have an alternating series. Now, having said that, if you don't have any more questions, or if you have questions later, email me. If not, I'll end the session here, and I have tons of practice problems for you guys for this midterm too. And I think Professor Katarzyna is also going an exam review next week as well. So for next week, the plan is that next week we're gonna do last minute review for exam 2. which I'm gonna go over the hard question in the practice exam. But last time, when I look at the practice exam 1, no one actually do it at the moment that I chose it. I mean, only 2 out of 50 people in the class actually did it already. So I would say in this midterm 2, please do the exercise and the practice, because I would say in this class what happened is that the material is going to get harder and harder, and especially for the final exam, I don't think you're gonna want to, not do the practice exam, because that usually is the most challenging part of this class. It just get harder and harder in this class, honestly. So please, please, please do the practice exam this time. All right. Having said that, um, I'll see you guys next week. Have a great week and happy studying.